We are now going to look at temperature and heat. These are related but different properties. Temperature is a measure of the average kinetic energy motion of particles in a system. Gas, liquid, or solid, doesn't matter. This is the motion of how fast the atoms and molecules are moving. So velocity. So as we're measuring average velocity of motion of these molecules. Temperature is an intensive property, meaning it does not depend upon how much substance we are measuring. So a cup of water has the same temperature as the swimming pool it came from. And temperature is also a measure of the direction that heat will flow. Heat will only flow from hot to cold temperatures. Heat will never flow from cooler to hotter temperatures. So heat only flows from hot to cool. So temperature lets us know for a particular material, particular object, higher the temperature, the higher the amount of heat in that object. But by comparing temperature to different objects, it doesn't tell us which one has more heat in it. And for velocity of molecules, there's going to be a range of velocity of molecules. So this left chart gives three different temperatures. So 273 Kelvin, we see a sharp peak, but we still see a tail running from 0 to about 1200 meters per second. So there's a wide range of velocities of the molecules. And we get a peak, and as we increase the temperature, we spread out the range. The peak decreases, gets more broad, the range gets bigger. So at 1273 Kelvin, velocities run from almost 0 to over 2000 meters per second. And at 2273 Kelvin, it runs from almost 0 to almost 3000 meters per second. So as we increase temperature, the range of velocities increases, but the peak gets lower and more spread out. For heat, heat is a total measure of the energy of the material. So heat is an extensive property. It depends upon how much substance is present. So a cup of water has a small amount of heat compared to a swimming pool. And we're able to extract the heat out. So we can extract a tiny bit of heat out of a cup of water. We can extract a lot of heat out of a swimming pool. But if we compare two objects that have the same mass or same volume, depending on what we want to compare, two different materials at the same temperature, they won't have the same heat. So heat is extensive, depends on how much material is present. It also depends upon what material is present as to how much heat is present for any particular temperature. And that's because the energy stored in a material, only part of that energy is truly measured as temperature. So we have other ways of storing energy in a material that don't show up just as temperature. Temperature is measuring the velocity, but it's not measuring vibrational energy, rotational energy. So we have ways that the molecules move inside themselves that hold energy also. We have two metric temperature scales, and of course we have the Fahrenheit scale that the US is still using. So we're going to learn how to convert temperatures between these three scales. So the zero temperature for each of these is at a different temperature. For Fahrenheit, there are two stories about how he measured or determined or set the zero temperature. One was it's the coldest temperature he got using salted ice water, and the other one is that it was the coldest temperature in Berlin during one particular winter. For Celsius, zero is the freezing point of water at atmospheric pressure. And for Kelvin, it's the lowest temperature possible in the universe. Lowest theoretical, lowest, we haven't broken it, so lowest temperature possible in the universe. We've gotten close to it. We've gotten down to a millionth of a Kelvin of absolute zero. So the zero Kelvin is called absolute zero because there is no possible negative kelvins. There's no possibility of going below that temperature. So 0 Kelvin, essentially all movement will stop. All translational movement will stop. All extractable energy will have been extracted. And some materials will have some base vibration that cannot be stopped. So we've talked about the freezing point of water. Let's go to the boiling point of water. Boiling point of water for Fahrenheit would be 212 Fahrenheit. Many of us are probably familiar with that. Boiling point of water is an easier number to remember. It's 100 degrees Celsius. Now, these zeros between Celsius and Kelvin are quite different. The temperature size, the degree size is the same. So as we increase the temperature 5 degrees Celsius, we increase it by 5 Kelvin. But the absolute zero is minus 273.15 degrees Celsius. So freezing point of water is 273.15 Kelvin. Boiling point of water is 100 degrees Celsius. So it'll also be 373 Kelvin. In room temperature, we like our room temperature to be high 70s. For Fahrenheit, that would be mid 20s for Celsius, and almost just under 300 Kelvin. So a couple of the bold numbers here we need to know. They're going to help us along. So absolute zero is 0 Kelvin. Freezing point of water would be 0 Celsius. Well, we also know it's 32 Fahrenheit. It's also 273.15 Kelvin. And boiling point of water is 100 degrees Celsius. So a couple of these other temperatures we're going to at least be able to get to rather quickly using our conversion units. So absolute zero, we'll be able to get to the negative 273.15 degrees Celsius. We're not going to worry about absolute zero in Fahrenheit. Boiling point of water would be 373.15 Kelvin, and 212 Fahrenheit also for the boiling point of water. That is used in creating our conversion between Fahrenheit and Celsius, but we don't actually use it directly in the conversion. So absolute zero, we get this from our gas properties. If we measure pressure, gas versus temperature, and then extrapolate down to zero pressure, we end up with absolute zero. Do the same thing with volume. Measure pressure, volume versus temperature, extrapolate down to zero volume, we get absolute zero, which is 0 Kelvin, or negative 273.15 degrees Celsius. So our conversions here, Fahrenheit to Celsius, we need one of these three. Either the second or third is what I would recommend. The first kind of shows where we get the conversion from. So our first step to convert Fahrenheit to Celsius is to subtract off the difference in the zeros. So freezing point of water is 32 Fahrenheit. It's also 0 Celsius. So we subtract off that 32 Fahrenheit. Then between freezing point and boiling point of water, there's 100 degrees Celsius, and there's also 180 degrees Fahrenheit. So we divide those by 20, we get 5/9. So we can use 5/9, or the other one is 9/5 is 1.8. So these are where the numbers are coming from. So we pick one of these. So we take Fahrenheit minus 32 divided by 1.8, and we'll end up with degrees Celsius. The reverse process, taking the bottom one, we take our degrees Celsius, we multiply it by 1.8 degrees, and then we add the 32 back on, and that'll give us degrees Fahrenheit. For Celsius to Kelvin, we just have to add the difference between the two zeros, since the degree size are the same. So to go from Celsius to Kelvin, we add 273.15 degrees. To go from Kelvin to Celsius, we subtract 273.15. And if you ever end up with a negative Kelvin, you did it wrong. Go back to the beginning and do it all over again. To convert between Fahrenheit to Kelvin, we could create one equation to do the conversion. But it's best just to do it as a two-step process. Have one equation, less to memorize. So to go from Fahrenheit to Kelvin, we'd go Fahrenheit to Celsius, and then Celsius to Kelvin. So an example here, so if we want to know oral body temperature, we know that the average is 98.6 degrees Fahrenheit. So we subtract our 32, we multiply by 5/9 or divide by 1.8, and we end up with 37.0 degrees Celsius. Now, significant digits, we should just keep the same number of decimal places for each of the temperature scales. So if we have one decimal place in our Fahrenheit, we should have one in our Celsius and one in our Kelvin. This table is just for your convenience. It's not necessary to memorize this table. Although there are some things on here we will need to memorize along the way, and they are pointed out in other parts of the lecture.